Success.
Alrighty, folks. Thanks everybody for joining. We're going to get started shortly here in a moment, just giving some folks some more time to join. We're expecting quite a crowd today, so we're quite excited. So give folks just another few minutes to join. All right, and hi there, Titus.
Howdy.
Great to see you. We'll
Thanks for
give
having me.
some folks another minute or two, and out here in Providence, or for those joining on the East Coast, you're in New York, it's a rainy day, so what else should they be doing, right?
Yeah, I liked last week a lot better. This week is gloomy and cold and bleh.
So let's just give it about 1 more minute or so, and then I'll introduce you. And I'll try to manage the questions as best I can. If you'd prefer to hold questions till the end, just let me know.
I'm totally happy either way. I always tell people jumping in with clarifying questions is totally recommended. But no matter how many times I say that, nobody seems to jump in. So we can do Q&A at the end. Whatever works. Like I'm really very non-formal. So
great. All right, you heard that, folks. That means come with good questions. All righty. So how about I do a little introduction for you, and then whenever you're ready, you can share screen or take over, however you like.
Sounds good.
So thank you everybody for joining. It's a real pleasure to have with us speaking today Titus Winters. He's senior staff engineer over at Google. He's been there for over 10 years, and he really has a unique perspective into software design. Just a few highlights that folks read when registering. He's in charge of over 250 million lines of code that are touched and modified by over 12,000 developers, if we can imagine that scale. And more recently, he has written and shared with us the book that you've downloaded, the book Software Engineering, which is known as the Flamingo book. So it's a real pleasure, Titus, to have you with us today, and I'm going to let you take it from here.
Great. I don't have screen sharing access.
After I give you the power.
Yeah. But yeah, you all very much for having me. It's really kind of one of the few sort of silver linings of the whole work from home era. It's a whole lot easier to do this sort of outreach without having to travel, and I think it's also kind of important. So hopefully you get some value out of this. I certainly enjoy doing these talks and having the Q&A time and the chance to connect with people. So like I said a minute ago, if you have clarifying questions especially, I'd love it if you raise your hand, jump in, ask for questions in the chat. And otherwise, we'll have plenty of time for Q&A at the end. So here we go. When I go out on customer visits or I give conference talks, I'm sometimes asked, what's the secret? Why is Google good at software? And that, of course, assumes that we are, and sometimes that is up for debate. But for the sake of argument, you can bear with me. I gave a talk a few years ago that included the following pitch. For the low price of $5 million, I will sell you a tool that will enable you to keep your code base happy and your developers productive forever. And if everyone in the audience chips in, I will grant exclusive access to this tool, and you can resell it however you want. And I think that this would be an amazing deal, right? Like, you all stand to make a massive pile of money reselling this product to everyone on Earth, and I get to go retire to a beach somewhere. And yet, no matter how many times I say this, nobody's ever going to reach for their checkbook, because even if this was a serious business pitch, nobody would buy it, because we all have a deep understanding that such a thing must be snake oil. It cannot exist. Why is that? And I think the hint here goes all the way back to 1975 with Fred Brooks and the Mythical Man Month essays. There is no silver bullet. There is no one tool or language or engineering practice that is going to provide a 10x productivity boost. Instead, it's a continuous slow march as we refine our technology, processes, ecosystem, and understanding. And we saw that with the site reliability engineering books. It isn't just one thing that takes you from the bad old days of spotty uptime, low reliability, early internet, and gives you Google-style reliability and performance. Instead, a host of changes are necessary. You change culture. You move towards blame-free postmortems, where you spend a lot of time to identify the root cause without pointing fingers, without it being a blame, without someone's job being on the line. Instead, if there was an outage, you have a unique opportunity to learn something important about where the risks and where the weaknesses in your technology lie. You also need changes in technology. In SRE terms, we do this with monitoring. We regularly say you cannot run a reliable service in production without monitoring. You need to know ahead of time how your service is doing. And we also even change how we conceptualize the problem. And SRE, this was moving to error budgets. And that one I think is particularly enlightening. Rather than say that the goal is for our site to be up 100% of the time, which is difficult, expensive, and causes everyone to be extraordinarily risk averse and isn't usually noticeable by users, instead we set a smaller goal of 99.9% or 99.999% uptime. And then we use the downtime budget to adjust our risk tolerance. If we've spent the budget for the quarter, then we need to be very slow and careful with our releases. And if we haven't spent it yet, then we can focus more aggressively on new features and experimentation. And that change of 1/10 or 100th or 1,000th of a percent in the goal changes the entire understanding and management of the problem. So taking a cue from the SRE books, I'd like to present what I think of as our core tenets, the ways that we're framing problems that I think make software engineering as we understand it at Google different and effective. These are the main themes and theses of the Flamingo book: time and scale and trade-offs. And these overlap very heavily with software engineering definitions and thinking that goes back to the earliest days of the term software engineering. Like Dave Parnas or someone in that crowd, the source of the quote seems a little disputed, said all the way back in the 70s, software engineering is the multi-person construction of multi-version programs. And multi-version captures this first, most critical idea, time. And that's what we're going to dive into first. How does time affect our projects? And the question that I like to ask most to get into this idea is, what's the expected lifespan of this code? It is important to realize that there are 6 orders of magnitude of reasonable answer to this question, and yet it's rarely discussed. Very often, if a novice is learning to program, the lifespan of the resulting code is measured in hours or days. These programs and code snippets are usually not touched again after their initial production. In some colleges, you might have a project course or a hands-on thesis. For most students, that project is the only time that they're operating on code that's going to live longer than a month or so. And that short life expectancy for code doesn't necessarily change immediately upon entering the industry. A very large amount of the tech industry is focused on startups, which have a notoriously short expected lifespan, between 1 and 3 years, depending on what stats you look at. And most of the effort at a startup focuses by necessity on keeping the business alive. You need to make it to the next round of funding. The company might not live long enough to reap the benefits of any investment in long-term sustainability. And then, of course, there's also apps and all sorts of projects that are thrown away after a couple of years, even at big and successful companies. But by counterexample, successful industry projects or open source projects may have an effectively unbounded lifespan. Nobody can reasonably predict an endpoint for the Linux kernel or the Apache web server. In most Google projects, we can't predict when we no longer need to upgrade our dependencies or language versions. And these long-lived projects have a very different feel to them than programming assignments or startup development. Another way to look at it, on the short end of the spectrum, if I'm just hacking on a Python script and a new version of my operating system comes out, should I stop what I'm doing and make sure that my script works with the new operating system? And I would say, no, that's bananas, right? You're in the middle of a thing. You're in a flow state. Spend the 5 minutes, finish your task. You can upgrade tomorrow or at the end of the day or next week or next month, right? It's not critical. But on the other hand, if I have code that was written at Google, in the early 2000s or pre-IPO, and we still haven't been able to update it to the current operating system or the current version of its language or libraries, that's unambiguously a signal that something is wrong. And together, even just these two extreme endpoints means that there's a scary transition in here. Somewhere around the 5-year mark, you tend to start getting into, yeah, this really needs to be upgraded. And that's unfortunately right on the outside edge of the experience level for most developers. Many of us have not worked on the same project for longer than that 5-ish year mark. Worse, the cost of paying down everything that built up in the project over those first years is particularly rotten for 3 main reasons, which I think all sort of multiply together. The first is that you have to overcome what we've taken to call Hyrum's law. Hyrum's law is, with a sufficient number of users of an interface, it does not matter what you promise in the contract, all observable behaviors of your system will be depended upon by somebody. This was originally sort of a throwaway observation. Hyrum Wright was one of our first engineers to really master what we've taken to calling large-scale change refactoring, our tools and policies that allow us to refactor interfaces that are used by tens or hundreds or thousands of callers. And it turns out when you see at scale the frequency that things just happen to work rather than actually being correct depending on what is promised, it sort of flips your reasoning a little bit. And this is what happened to Hyrum, right? You can wish that people were more disciplined, but you realize that it's not going to happen. You're spitting in the wind. Understanding Hyrum's laws. One of the major remediations that we have found against Hyrum's law is non-determinism. If users of your interfaces can't reliably depend on your behavior, then they won't. So if you don't want to promise a particular behavior, randomize it a little bit. And this comes up in all sorts of places, but the easiest one to describe we've found is hashing. Countless subtle dependencies exist on the current hash behavior in many programs. Changing the hash function or changing the default container size, changing anything about your hashing is going to change the order that those elements are returned when you iterate over the contents of your hash table. And that's a drag because hashing is central to efficiency in modern big software. And the constant march of technology means that there are new approaches to hashing all the time, hash functions, new container layouts. And you'll not be able to deploy those improvements if people are depending on the hash iteration order. So instead, languages and libraries may come up with ways to add some non-determinism to prevent that. Randomness is therefore a mitigation for Hyrum's law. But it's only a mitigation because just like entropy, you can't win. We saw this with the Go programming language. Hashing has been randomized in Go for quite some time for exactly this reason. And that gives the Go team the capability of making changes to the container for performance reasons, or even just to clean up the code. But we've also found that people depend on this behavior. One bad way to shuffle a sequence of elements is to throw all of those elements into a hash and then iterate through it. Turning off the randomization, turning off the Hyrum's law mitigation will break the users that came to depend on it. You can't win. You can't even break even. So the first major point in why are upgrades hard, especially this first upgrade, is that you have to shake out all of these hidden dependencies, everything that anyone has done over the first 5 years of your project that wasn't entirely principled, but that worked. And that can be anything and everything, right? If you haven't changed things in your dependencies for 5 years or more, then at scale, you're going to find all sorts of nasty lurking. But we do find that these build up slowly and consistently, right? If you shake it out and you keep shaking, it's possible to keep it at bay. The second major difficulty is that you're treading new ground. By definition, you're doing a thing that hasn't been done to this project before. You won't have policy in place to decide what is safe. You won't have experience on the team to fall back on. You're setting new precedent. And that's always hard, both technically and organizationally. And lastly, we say, oh, hey, we're upgrading now. Let's go all the way to whatever is current. So those long deferred upgrades tend to be, we're going from version 1 to version 5 instead of the nice incremental go from version 5 to version 6. That's more change to absorb, and therefore also inherently hard. I think each of these three items individually makes a task like an upgrade, a big change, challenging. But they're not independent. They each make the others more difficult. And so the multiplicative effect is very challenging. And thus, after doing an upgrade once or giving up partway through, it's pretty reasonable to overestimate the cost of doing the next one and just decide never again. And you commit to always throwing things out and rewriting. This is why software is constantly being revised. But getting through not only that first process, but getting to the point that you can reliably stay current going forward is a big part of what I think of as sustainability. Sustainability for software is the idea that for the expected lifespan of your code, you're able to change all of the things that you ought to change, and you can do so safely. And this hides a lot of nuance, right? Because we're talking about the expected lifespan. We're talking about, are you able to, not whether you bothered to do so, and how much do you put weight on what you ought to change, and how safely, right? There's a lot of subtlety in all of this. And one of the biggest and most important points here is for long-lived projects particularly, making the transition to sustainable is going to be awfully challenging. Whereas for very short-lived projects, over the expected lifespan of that Python script I was talking about a little while ago, there's nothing that I ought to change. And so you get sustainability right out of the box. So when someone like Google says, this is how we do things and why, some chunk of that is going to sound like utter nonsense, right? We're adding all of these extra steps and safeties and policy that are never going to be necessary, never going to pay off, right? All of your experience might say, hey, I've done perfectly fine at building all of this software and none of this was necessary. But it's a different thing when you're on a very long-lived and sustainable system because you're playing a different game with different best practices than you would on a more short-lived programming project. I also happen to think that a lot of those practices do pay off in the short term and will serve you as you grow, but I'm only going to fight you on the long-term ones. So in the same way that SRE pushes people to realize that error budgets is a better way to define the problem, software engineering is about realizing the production of software is not the goal. It's not even really the interesting part. Solving problems and keeping those solutions working for as long as is necessary, that's the real goal. And this is our first pillar in understanding software engineering. Be mindful of time. There are hard problems in programming, to be sure, but those are largely challenges in execution, writing bug-free code, understanding the problem that you're solving. It isn't until you add time to the mix that you start running into problems that are actually really nasty, that you couldn't plan for, that you're just going to have to wing. Version skew, merge conflicts, race conditions, schema evolution, backward compatibility. So much of the really subtle and unpleasant stuff has one underpinning commonality: time. Time is the hard part. Time is the extra dimensionality that takes our nice, understandable programming problem and makes it into something nasty. Software engineering is programming integrated over time. If you're successfully making things last, then the next thing that you need to start worrying about is what happens if you start to grow? Where do you start to fail? And as your organization grows and ages, if you're successful, Are the things that you're doing as part of your software process scalable? Right? If your project doubles in scope and you have to perform some labor-intensive task a second time, like that upgrade, is it going to be twice as labor-intensive, or 4 times, or can it be cheaper? I'm just going to claim everything that your organization relies upon to produce and maintain code should be scalable in terms of general cost and resource consumption. We talk about CPU and RAM and disk and network and all of these things, and there's plenty of optimization and scaling discussions to be had there. But I think the more interesting part is everything that your organization is doing repeatedly, in particular, must be scalable in terms of human input. Pay attention to your humans. No task should require increasing heroics as your team or code base grows. No task should require broadcast messaging or superlinear communication scaling in order to just produce software. And importantly, there are going to be plenty of tasks that can be solved by approaches with bad scaling, and they may even work fine early on. The problem is that you're going to have to track them and be ready to move away from them to something that scales more smoothly. Time and scale come together in odd ways. So we'll start with an example of what Google mostly has learned about deprecation and churn many years ago now. A traditional deprecation, you might say, there's an old thing, an old function, an old class, an old database system, whatever, an old interface. And we don't like it anymore. We want everyone to move to the new thing. So one thing that a company might do is mark the old thing deprecated, introduce the new one, and just ignore it, right? And the problem with this over time, over a long enough time period, is that as new versions are introduced every 2 or 3 or 5 years, then without a forcing function that actually pushes the old and unmotivated users off of the old thing, which from their perspective is working perfectly fine, then you're going to wind up with an ever-increasing amount of maintenance for purely legacy systems. Sometimes this doesn't matter, right? Having 2 versions of a function in your code base isn't actually a lot of maintenance burden for that library maintainer. It doesn't really matter. But higher level interfaces have increasing costs, both for the maintainer and for the ecosystem at large. Storage systems and microservices are particularly nefarious here. Yes, it's going to cost you something upfront to push developers off of those older systems, but sometimes that total cost might be less than the ongoing legacy maintenance of running 2 databases or microservices or whatever you're doing, especially when ongoing might mean indefinite. You might be talking decades. Another thing that might be done for deprecation is you just force people off the old thing by scheduling it for deletion or turn down. But mandating that everyone update also kind of doesn't scale well, right? If you look at graph growth algorithms, for instance, as the code base expands, leaf projects, those that no one is depending on, but that depend on things within your dependency tree, those leaf projects have an ever-growing set of dependencies below them. And if every one of those has the right to say, all users, everything that depends on us transitively must move from the old thing to the new thing by the 1st of June, then you're increasingly forcing all of those leaf teams, all of those project teams, product teams, to run just to stay in place. And annoyingly, on each of those teams, some individual is going to get stuck doing the work in those projects. They have to learn all of the details of this migration. As a large organization, you might be paying for that ramp up, for that learning, for that first time mediocre execution over and over and over and over again. And if you do this to your external customers, that's even worse. And the worst of all is that most projects that depend on your database system aren't actually leaves, right? Other things also depend on them as well. This means that your threat is disproportionate, right? Especially in a continuous development, continuous deployment, trunk-based, mono repo sort of world. You aren't just breaking the build of the project that didn't listen to your threat. You're breaking everyone downstream of them. So I might compare this to a real world analog. Timmy, if you don't put away the dishes, I'm going to blow up the city. This might get the dishes to be put away, but if it doesn't, then either your threat was false or you're primarily harming bystanders that had nothing to do with the great dish debacle. And if your policies about code-based maintenance are primarily based on harming bystanders, it's probably not the best policy. You could also resort to heroics, have just one person fix absolutely everything, but heroics don't scale either. And this particularly doesn't work when you don't have perfect visibility into all of your users. If you don't have a mono repo or the logical equivalent, this is going to be out of the question. Instead, at Google, we try to hold to the churn rule. The majority of the cost of any change to your interfaces, any change to your systems, must be paid by the team that is making that change. There needs to be a published and reviewed transition plan. And this is going to constrain designs for the new thing. But this also puts incentive structures into the right places. And buried in here is an important point, because practically speaking, policies like this scale better specifically because of knowledge, expertise, and communication within an organization. These things have very good payoff, often with a superlinear effect. That is, when you force the team that is triggering the change to be specialists that understand how to execute the change, it's a far cheaper outcome in a world where all of your users are visible to you, at least. Right? You're only going to pay the ramp-up cost a couple times, and then expertise and automation make things quick and cheap. In a successful organization, everything that must be done repeatedly must consume sublinear resources, especially sublinear human effort and communication. We also need to worry about code base size and build and test resources. The growth rate on all of these types of things tends to be slow but steady. Right? You might want monitoring for your build times over weeks and months and years. You want resource consumption tracking to have a good idea of where you are and to help prevent boiled frog problems. Monitoring your human processes for things that are becoming all-consuming for some poor heroic soul is even more important. Superlinear scaling for any cost is a serious risk for an organization. But on the flip side, the same properties of scale that make those costs dangerous make the hunt for scale-based efficiency extra potent. In a well-functioning organization, many tasks, especially those that don't become necessary right away, can be carved off for experts, compiler upgrades or operating system changes, API migrations. And the impact of those experts tends to be superlinear because of accrued expertise, automation, familiarity, etc. To say nothing of when you shake the tree and unbreak all of the Hyrum's law problems, that always helps too. When it comes down to it, you must be aware of scale, right? Don't fear it, but respect it. It's a sign of success, after all. For another glimpse into how does this scale, consider version control policies and merging. It is not rare to encounter shops that have very strict policies around who gets to merge into trunk and when. And it's not even hard to understand why. A team might be off developing on a branch for a month, they finish, they merge, and then you find that the release is unstable. Everyone has seen this. Big merges can be costly. And when you're approached with a problem like that, as a team, as an organization, you have two options. You either control that cost, you lock it down, or you figure out how to make it cheap. You practice, you reduce the cost, you make it common. Depending on the situation, either of those could be good. But for version control the cost path is bad. And there's an increasing body of research that shows this. And I think this is the perfect microcosm of what I mean by watch out for scaling problems. Companies that I was involved with before Google absolutely relied on this sort of merge strategy meeting with different teams and different contractors that were all working on long-lived dev branches. At one point, we even had to hire an additional content management engineer to handle the load for merge and retest operations, because when we got to 200 engineers on the project, the one guy that was in charge of merging things couldn't keep up. Adding a second engineer to him didn't double the throughput on merge operations because the two of them had communication and coordination overhead, just as predicted in every engineering text for the last 50 years. By comparison, Google has a couple hundred times that many full-time engineers. Nobody is responsible for the merge. It just works. And it isn't that our engineers are that much better, it's that we spotted that this policy wouldn't scale because there's too much coordination. And we found something that required fewer decisions and thus less communication and coordination. Another example of time and scale playing together could be seen as shifting left. In the past decade or so, this idea has emerged that has become a real common touch point in software engineering or DevOps methodology. Shifting left makes things cheaper. The earlier in the software workflow that you can catch bugs, the cheaper they are. And I see this as a direct result of thinking about systems, thinking about the policies that go into your engineering workflow in terms of time and scale. Originally, this shift left was phrased in terms of shift left on security. As an industry back in the early 2000s, it was very common to see, let's think about security tacked on to the very end of the software process. And as it turns out, that's very expensive. Software that's already been released to the world is constrained. It's hard to change. It's dependent upon. Security bugs in the wild have legitimate real-world consequences, potentially up to loss of human life. Catching those same bugs before that software is released into the wild is much cheaper. Users aren't depending on the feature. You don't have the same legal liabilities. You can fix it and try again. You might still have to pay for testing and canary release costs, but that's still a whole lot cheaper. And it'd be cheaper still if you caught it in code review. Right? The developer responsible knows what they were trying to do. They've already got the details fresh in their head. Languages like Rust are prioritizing making it hard to even express the riskier concepts, pushing this focus on security all the way back into the development step. The same basic principle applies to bugs of all forms, not just security. If a bug shows up in Canary, that's better than it being released, but now you have to look through all of the changes since the last release to see what broke. If you catch it pre-submit, you know exactly what broke. If we catch it during development, it might not even register as a hurdle during the developer's work. So we add steps to the workflow, usually in order to catch defects earlier and cheaper. But you have to be aware that the purpose of those steps is never 100% defect reduction, because that's impossible. Bugs are always going to slip through. The only truth, the only high fidelity indication of being defect-free, or at least defect neutral, is to run directly in production or to deploy to users. And the costs and risks inherent in doing that are very, very high. So instead, we add all of these proxies, trying to balance cost and time delays and fidelity for each possible class of defects. And I think that this ties nicely to both time and scale. Right? It's a time issue. Imagine you were building two houses. One construction company has alarms in place that detect when anything in the construction was done in an unsafe fashion, and it sounds the alarm instantly. The other company has detection that is just as accurate, but the alarms only go off on move-in day. Which house would you buy? Heck, which house would you rather build? But it's also a scale issue, right? Even if you handle time perfectly, and you move to a world where you have push on green, continuous deployment, you can submit a change and instantly see it in production if the tests pass, it's still going to be cheaper to find bugs earlier in the process because you don't have to worry about, was this change, or was this problem caused by me or someone else, or the interaction of our two changes? So scale, interacting with other humans especially, is the second important pillar when considering tools and policies and practice in software engineering, or anything really, but I think it's particularly acute here. So considering these ideas of time, how things are going to change, and scale, how your team and your org and your workflow are going to function as you grow, I think all that's really left is make good choices, make evidence-based decisions. If you understand that change must be possible, if you're explicit about the lifetime for your software that you're producing, that you're maintaining, and you understand the scaling goals of your team, of your organization, and your engineering process, all that's left is to focus on making good decisions. People often say that everything in engineering is about evaluating trade-offs. And we find that that is still true in software. The important thing is to make data-driven, or at least evidence-driven decisions, accounting for the realities and the requirements of time and scale. You have to aim for sustainability. You're going to make thousands of small decisions in software design, in engineering policy, but if they're done with a goal of sustainability for whatever the expected lifespan of your project looks like, then you're going to be in a better place. But change has to be possible. No superlinear scaling, especially for humans. And critically, because time and scale both have a tendency to change things, we need to reevaluate from time to time. The context changes, and the reasons, the evidence that goes into any given decision will change over time. A decision from last year may have been right then, but it may become wrong next year. It's reasonable to summarize all of this as make logical trade-offs. In many respects, it shouldn't need to be said. Of course, you want to make logical choices if you want good outcomes. But this is less about a surprising insight and more about focusing on an important philosophy. Within Google, there's a very strong distaste for because I said so. Inherent in all of this discussion is the idea that there needs to be a reason for everything. Just because, or because I said so, or because everyone else does it this way, are places where your very worst decisions lurk. So what's the secret? It's these three things, right? Software engineering is more than programming, it's time. I think it's actually a different dimensionality of a problem. I talk about squares aren't cubes, velocity is not acceleration. In exactly the same fashion, software engineering is not programming. They are different dimensionality. Be mindful of scale. Superlinear scaling is bad for required processes, but expertise and specialists' knowledge can have a equivalently large impact in their domain. And make good choices. Don't rely on because I said so. And remember that the evidence is going to change over time and you will have to reevaluate. And it is not a mark of a failure to have to change your mind or change directions. That's the mark of a strong leader. The book, the Flamingo book as a whole, this talk is basically the first chapter. And then we move directly into the most important stuff, which is culture, right? How to be a good teammate, how to be a responsible engineer, how to be a good leader. And we discuss a lot of policies and processes of how we try to think about things and organize our systems so that they work together smoothly, and a little bit of the tools and technology that actually goes into holding it all together. And I will leave you with the final idea. It's programming if clever is a compliment. It's software engineering if clever is an accusation. And when you understand just how true that is, then you probably are a software engineer.
All right. On behalf of everyone, Titus, thank you very much for that excellent talk. We'll give you the biggest virtual applause possible. And I would like to spend this time to open it up with questions. I think if folks can type them in the chat, that's probably the easiest way. And then maybe I can read them to you, Titus. I've actually got one that I want to start us off with because I think about this when I teach our software engineering course. And we talk about agile development, waterfall, user stories, and sort of planning. Something I've never done, though, is had as part of those user stories the expected lifespan of the code. And I'm wondering, now I might shift that, but I'm wondering if that's something you do at Google and if that's something that's sort of reprioritizes the tasks based off the expected lifespan.
A little bit.
Is that a metric you've seen? Okay.
A little bit. One of the things that makes it a little odd is sort of, we have a monorepo, sort of famously. Like there's hundreds of millions of lines of code, billions when you count across all languages. And as it turns out, by default, people don't delete things. It is much, 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 much harder to unengineer something than to have written it in the first place, because there are subtle dependencies that spider out across the whole code base. And so there's kind of relatively rarely a really solid like impact story, like bang for the buck for going through and actually deleting everything. And one of the side effects of that is by default, if you're working in the code base that basically everyone is working in, your code is probably going to live for decades. Like there's no question there. There are a handful of programs that we have, things like internal startup incubators and stuff, where they're very explicitly giving you much more latitude, much more freedom with the expectation that you work for 6 months or a year on your project, and then they decide whether to launch it or not. For those sorts of things where you have that much more concrete and limited lifespan, we do give them some extra flexibility, some choice in the matter. But what we have found more so than anything is, even over the course of a year, it's almost certainly still in your best interest. Like write tests, have people that know what they're doing review your code. It is not actually going to slow you down. Certainly not over the course of months and months, right? If it was a matter of like, hey, we're going to be canceled in a week, 2 weeks, like, yeah, maybe, like you can cut some more corners there. But I actually think that the payoff rate for a lot of these sorts of policies and best practices is a whole lot shorter than a lot of people would guess. I think it's going to be weeks or very small number of months for almost everything. And we'll see that become more common through the industry. Like when I started talking about tests for maybe 8 years ago, I think less than a quarter of the people in the audience would tend to say like, oh yeah, we write tests. These days it's up to at least half, right? Like the norms in software engineering change, which should not be surprising. It's only 50 years old, right? Like I'm not that old. I've been a programmer for half as long as that term has been around. Like,
yeah, certainly. Awesome. Let's see. So we've got a few questions queued up here. So I'll start with Muhammad's question. Do you have any advice for young software engineers starting their career on how to get on the right foot for success, besides, of course, sticking to the principles you've discussed?
I think the two biggest pieces of advice that I have are practice. Software, like programming, thinking about tech, all of this stuff is a skill like anything else. And it's going to just take a lot of practice to actually like achieve mastery there. I often think that learning to be a programmer, learning to be an algorithmic thinker is at least as much of a cognition change as learning to read, right? And you did not do that in 4 years of, one course quarter, right? So you want to practice. It will pay off. And then the second, and I think maybe more subtle thing is the difference between software in school when you're learning to program and software professionally is you're not going to work by yourself like ever again. Everything that you do in school is very much like, we have to give you a grade. We need to know that you did the work. We need to know that you have absorbed how to be a programmer. That all makes perfect sense, right? It's important. But like day one, when you get to a job somewhere like Google, the rules change entirely, right? We don't want you to go off and like work on your assignment for 2 weeks before you show it to someone. We want you to probably go like an hour between checking in with your team to see if you're on the right track. And that takes a huge change, right? Software engineering is a team sport. And the other part of that that's super important is communication and learning to be a nice person, learning to be a good teammate. That's critical. Like I can train you to be an amazing programmer. Like that's fine. Like if you come to me with basic programming skills, I'll make you a world expert in a year. I can't teach you to be a good person, right? So when it comes to interviewing, one of those I focus on a lot. One of those like, oh, you passed the bar, that's fine, right? So anyone that's really like, I don't care about people, it's only tech, like, no, sorry. Like you're off in the weeds. Yeah.
I think that goes great with our next question. Scott is asking, what are some non-technical related skills that you think are key to being successful as a software engineer? So some of the ones you mentioned.
Teamwork, communication. I have a very weird job as a software engineer, and I write more essays than I write code at this point because there are so many lessons that I've learned, and like I don't want everyone else to have to learn it the hard way. And it's vastly more impactful for me, like if we can publish better understanding and best practice guidance for testing. 50,000 engineers at Google are impacted by that, right? It's going to be really hard for me to sit down and write something that changes the efficiency of Google in the same way as that. So as it turns out, take an English class. It's kind of important. Like, I wish that I had been a better writer before I got into software. Weird.
Technical writing. Yep. Let's see. Next question coming in from Nishant. How would you recommend developer time spent on building fast versus building robust? I think this is in terms of performance. Fast versus sort of software that works.
I think it depends a lot on what you're aiming for, right? There are a lot of things that, like, if you know that this is going to die in a year or a week, like, it doesn't matter, right? Like, throw it together. If it works, it works. Like, I'm not going to argue that. If you know that it's going to take that it's going to be around for a long time, then you need to slow down and you need to read the docs and you need to know what is actually being promised and what you can rely on. Because especially in most of the tech industry where you're just going to like pull down some random open source project to solve your problem, you have no idea what that open source project's promising for compatibility over the long term, right? If they change their interfaces wildly every couple of years, that could be a real problem for you over, a 10-year lifespan. If you do something really clever, embarrassing. I thought I was very, very clever. I guess it was clever, not in a good way. When I was in grad school, I was working on some system and I wanted I needed to save a bunch of the data that I was like processing. I was like, I'm already writing all of this in Python. I'll just pickle it. And I can just dump the pickled serialized Python objects to disk. And then the problem was, like, this introduced a time issue because I changed the data format that I was like processing and how I was storing it. And then when I was reading stuff back, it wasn't compatible anymore, right? So like I caused myself this problem because time is the hard part, right? Clever, right? If you're doing something really short, be as clever as you want. If you're doing something with any meaningful length to it, clever becomes a really bad word really fast.
So going back to that first principle on lifespan of code and time. Yep. Let's see, another question coming in from Tran. Let's see. How do you work with product managers and distinguish between their priorities and your team priorities? So this sounds like working across teams.
I'm the worst person to ask this because I am kind of the troll that lives in the basement. Like my teams maintain all of the like basic common library infrastructure stuff, like, data structures and mutexes and caches and string manipulation routines. And product management doesn't super care about like the user affordances of all of that. Like it's kind of not their thing. So I have meaningfully less exposure to product management than most. So I can't give you anything intelligent to say about that. Sorry.
Let's see. Let's move to the next question here. Let's see, from Maham again. Let's see. One of the goals of Agile is to have knowledge sharing within the team.
Yeah.
Ideally, anyone can work on any ticket. However, I haven't found that this is super successful. Usually, front-end people pick up front-end tickets and vice versa. How do we actually knowledge share to achieve this goal?
I think it's one of these things that is important to aspire to, but it's not going to actually play out exactly that way in practice. It's also kind of important to realize like the front end back end distinction applies a whole lot more when you have a much smaller sort of product surface that you're working on. If you compare something like Gmail, right, there's going to be I'm guessing dozens of engineers that are just primarily working on front end issues, and a completely different set of people on completely different teams that are doing a lot of the like back end, algorithms and storage and processing and all of that stuff. And so some of the, hey, anyone on the team should be able to do that might be a matter of that becomes more true at scale. But even then, it's going to depend on like how large and how staffed your project actually is. The team that I'm most tied to has about 20 engineers on it, and they are not interchangeable. The thing that works very well to our advantage is not everyone on the team should be able to do all of these things. It's everyone on the team should know who to talk to for any given sort of problem. And couple that with don't have the like most expert person do anything, right? Your goal is not have this problem solved by the person that is most expert in it. Your goal is actually have this problem solved by the person that is least expert, but still capable, right? Because that is how that they are going to grow. And if you're doing this on a solid team with good support systems and good code review and all of those things, like any issues that might be like introduced by having someone with less expertise are going to get caught. And those are a learning opportunity, and that's just how growth happens. If you do that well, then you do get into a world where, yeah, there's plenty of expertise, plenty of diffuse knowledge. Like you don't have a really like bad risk factor for one person being sick or on vacation. So.
I think that goes back to some wisdom about with your product managers and building your team there. Yeah. I like that. Yep. Let's see. We've got a question here from Rashan saying, if one follows your argument for emphasizing scalable engineering processes, what then do you think is the next toughest challenge on the horizon for software engineering?
Dependency management. Figuring out what we're going to do about the fact that like modern software these days, you're going to go download like 5, 10, 500 open source packages that interdepend, and there is no guarantee any of those are bug free. There is no guarantee that any of those aren't about to introduce some sort of terrible change that breaks the build. The semantic versioning systems that we use are somewhere between idealistic and just flat out lying to us. Like we don't really have good systems in place for deciding what software controlled by some other entity with different priorities can we rely on over the long term. The open source world is great for solving short-term programming problems. And because of a heroic amount of effort from like distribution maintainers for your package management systems, crates in Rust or npm in Node, or your Linux distro like apt-get, those sorts of things. Because of a heroic amount of work there, like we sort of cobble it together in a way that basically works, but it's not scalable. And the dependency stack is getting larger and larger and larger. And like I'm deeply concerned. I had nightmare about writing that chapter in the book, quite honestly. And as far as I can tell, that chapter is just kind of depressing because every option is kind of hopeless. Like we just don't have good solutions here. That will be the challenge for the next 25 years.
All right, next question from Nate. I often hear an argument that young engineers should begin their careers at larger companies versus starting at startups. Oftentimes, it's the argument that some startups teach engineers how to do things incorrectly without having time, scale, and trade-offs in mind. I assume you agree with this. From your experience, how hard is it to unlearn bad skills learned early in your career?
No,
any wisdom on that?
I don't think that's necessarily true. Like, I think you are going to cut some corners working at a startup, but it's as long as you're aware of that, that's fine. And I think that there's a wide disparity in startups between those that are like, rah, rah, we're just going to check everything in and no tests and no code review and everything's just chaos and we're so cool, we'll just make that work. I rolled my eyes very hard there. There are startups that are plenty disciplined and have good practices, but are keeping in mind, like, yeah, we're probably going out of business in 2 years. I'm not going to worry about all of these long-term things. Like, that's perfectly fine. I think there's plenty that can be learned in either domain. I think there are some sides to going straight to a place like Google. You don't have a really realistic understanding of what the working world is like in a lot of respects. And some of the ways that Google's like infinite scale manifests, like, I don't understand what numbers mean anymore. I've been here too long. Like, you say like, oh, I'm going to use 10,000 computers. Like, I legitimately can't tell you if that's a lot. Like, I think it's not, but I don't know anymore. You might want to have some like practical hands-on experience before you lose that sort of touch with reality. So I don't think there's a right answer here. Like, find people that you like, that you think you can learn from, and find a company that you believe in. Like, that's, I think, the best advice.
Excellent. So these next two coming in from Diego and Pablo, I think they're the same. So I'll read one of them. Compared with studying algorithms or learning to use a new tool, learning software engineering is sometimes difficult because of its scope. Are there any specific exercises, practice tips, or resources that you'd recommend for learning software engineering principle skills?
I'm going to be a little heretical and say I don't think so. Like, if I'm talking about, software engineering is programming integrated over time, right? There's barely enough time in a 4-year curriculum to learn to be a programmer, right? You can't also learn a thing where the stakes only kick in over years, right? There's just not enough time to make time an interesting thing. And so I think in a lot of respects, and a big part of why I wrote the book and I'm trying to do this sort of outreach, in a lot of respects, the most important thing that you can do, from my mind, to advance your understanding of software engineering is to learn to think about like the problem in these terms, right? I'm not saying that just programming is wrong. Just programming is the right solution to an awful lot of problems. But you have to be very, very acutely aware that there's going to be a different class of problems that you encounter. But the first 3 weeks that you're on the job, you'll have more hands-on time being faced with these things than you're going to get in a class. And so I think in a lot of respects, like, learning how to think about the problems and learning how to talk about the problems and like learning the squishy theory that the industry is only sort of figuring out. I think that's probably kind of the right approach until you get that job. And then you just have to try to absorb everything as quick as you can. It's going to be a big change.
All right, so I want to watch the time, and we have time for about one more. And then I'll give you the last words of wisdom. So this last question comes from Victoria. And I don't know if this will be a short or a long one, but what does a day at work look like for you, Titus?
It changes. For me, I probably spend the first couple hours like drinking coffee and dealing with email. I try to keep a pretty active eye on our internal communities for C++ users in particular. So people will ask questions about design or bugs or all sorts of things. And I'll try to, spend a fair amount of time answering those sorts of things. There's a internal sort of hands-on mentorship program called Readability that we use for language expertise. So I serve as a C++ readability reviewer. Most mornings I'll have 1 or 2 readability reviews in my inbox. So I'll go through and like scan those, see if anything jumps out at me, like try to explain like where they might be going wrong, look up citations for best practices. If I find myself writing the same explanation about something over and over again, then I'll make a note that I have to go write an essay so that there's a citation for this. I manage an organization of about 35 people these days. So I have a lot of like one-on-ones to check in on people, especially during the pandemic. We spend a lot of time on like, how are you doing? Like try to make sure that everyone is, focusing on self-care and mental health and things like that, because it's tough. And then I tend to wind up like absorbed into meetings or things like that. It's been a couple years since sitting down to write code felt like the most impactful thing for me. But I have an unusual job, so that is quite different. One of my reports, one of my partners, who actually is similar level, like same sort of overall rank. He does a ton more programming directly, and is responsible for things like, oh yeah, and we deployed this change, we improved fleet efficiency by 1%, which when you scale that up to Google sizes, like that's a few machines. So I think asking anyone what their typical day is like, you're going to get a wildly like random sample, because it's kind of all over the map. And I care a whole lot more about doing these sorts of things, so my biases are a little odd. That's me.
All right. Well, Titus, on behalf of all the faculty, staff, alumni, and most importantly, the students here, thank you for your time and for joining us. We learned some valuable lessons and really appreciated the Q&A. And we're going to leave you with the final word before we end the call. Any last words of wisdom?
Like I said earlier, I think it's really, really important to remember that being a good person matters. It will improve your technical outcomes rather dramatically if you can have a team that has your back, and you're only going to actually get that if you are pleasant to be around, if you are a good team member. And that, I think, underpins a lot. Tech has its fingers in everything in the world these days, right? Like we can commonly talk about products that are affecting 1 billion people, and understanding the importance of where we sit in the world and the responsibility that brings, and recognizing that success in that actually starts with being a good person from the start. I wish someone had been able to tell me that when I was an undergrad. Like, so that's where I'd go. Like, focus on good.
Well said. And there you have it, folks. The last word from Titus Winters. Thank you again.
Thanks so much.